In present discussion, we are going to see preparation, characterization and applications of nanocrystalline mixed metal chalcogenide thin films. This is the chapter scheme of today's discussion. In first chapter, introduction and theoretical background. In second chapter, thin film technology. And in third chapter, thin film characterization techniques. And in fourth chapter, we are going to discuss synthesis and characterization of molybdenum bismuth copper selenide nanoflex thin films. In chapter 1, introduction and theoretical background, introduction to chalcogenes, metal chalcogenides and their applications, binary metal chalcogenides, ternary mixed metal chalcogenides, quaternary mixed metal chalcogenides, aims and objectives of present research work. What is chalcogenes? Four heaviest elements of the sixth subgroup of the periodic table, namely oxygen, sulfur, selenium, and tellurium, are collectively referred to as the chalcogenes. What is metal chalcogenides? Compounds containing a chalcogen element as an anion and metal as an cation are commonly termed chalcogenides. These are the several applications of metal chalcogenides. These are the aims and objectives of the today's discussion. In chapter 2nd, we are going to see thin film technology, that is introduction and thin film deposition techniques. In introduction, what is thin film? A microscopically thin layer of material that is deposited onto a metal, ceramic, semiconductor, glass or plastic base ranging from fractions of a nanometer to several micrometers in thickness is known as thin film. Special properties of thin film may differ from their bulk counterparts. Thin film technology is based on three foundations: fabrication, characterization, and applications. These are several thin film deposition techniques. The complete characterization of thin films can be done for optostructural and morphological characteristics such as phase analysis, compositional analysis, structural elucidation, microstructural analysis, and surface characterizations, which have strong bearing on the properties of material. Various methods used for characterization for these films are as shown in table. In chapter 2nd, we are going to see thin film characterization techniques. Introduction, thin film characterization techniques. These are the different types of characterization techniques. In physical technique, surface profilometer for film thickness. In optical studies, we are using UV visible NIR spectrophotometer. For structural analysis, we use X-ray diffractometer. For morphological studies, we use SEM, FESEM, TEM, and HRTEM. For compositional analysis, we use EDS and X-ray photoelectron spectrophotoscopy. And in electrical transport, where this is this technology. In chapter 4, we are going to see synthesis and characterization of molybdenum bismuth copper selenide nanoflex thin films. In this, synthesis of MOBI2AC5 and MOBI-CuAC4 precursor by arrested precipitation technique, that is APT, deposition of nanostructured MOBI2AC5 and MOBI-CuAC4 thin films, then results and discussion of MOBI2AC5 and MOBI-CuAC4 thin films, and then conclusions. This is the synthesis of MOBI2AC5 precursor by arrested precipitation technique. In this, all the chemicals used for synthesis of MOBI2AC5 and thin films by arrested precipitation techniques were of analytical reagent grade and used without any further purification. This is the synthesis of MOBI2AC5 precursor by arrested precipitation technique. This is synthesis of MOBI2AC5 precursor by arrested precipitation technique. This is the optimized preparative parameters for synthesis of MOBI2AC5. This is the reaction mechanism for synthesis of MOBI2AC5 precursor by arrested precipitation technique. This is the optimized preparative parameters for vacuum evaporation of MOBI2AC5 thin films, that is the precursor is MOBI2AC5 prepared by APT, melting point is 90 degrees Celsius, deposition rate, pressure, current and growth substrate temperature is at room temperature. This is the schematic mechanism of nucleation process of thin films by vacuum evaporation. This is the characterization of MOBITSC5 thin film by using characterization techniques, optical absorption studies, X-ray diffraction studies, morphological studies, topological studies, and compositional analysis. This is the optical absorption study. Plot of optical absorption spectra of as deposited and vacuum annealed MOBI2SC5 thin films in the wavelength of 350 to 1100 nanometer, while in plot of alpha h mu square versus h mu for MOBI2SC5 thin films deposition on glass substrate shows band gap 2.07 electron volt and 1.87 electron volt for as deposited and vacuum annealed technique. This is X-ray diffraction studies for the MOBI2SC5 XRD patterns of as deposited and vacuum annealed MOBI2SC5 thin films. This is surface morphological study. FESEM image of MOBI2SC5 as shown in A as deposited thin film, B shows for cross-sectional image, C shows for vacuum annealed at low magnification, and D for vacuum annealed at high magnification. This is the surface topological studies. TM images of vacuum annealed MOBI2SC5 thin film. A shows SAED pattern, B shows TM image, C and D HRTM images of respective places. This is the compositional analysis of XPS spectra of MOBI2SC5 thin film, survey spectrum, core level spectrum of molybdenum, core level spectrum of bismuth, and core level spectrum of selenium. Synthesis of MOBI CuSE4 precursor by arrested precipitation technique. This is the synthesis of MOBI CuSE4 precursor by arrested precipitation technique. These are the optimized preparative parameters for synthesis of MOBI CuSE4. Deposition of MOBI CuSE4 thin films by vacuum evaporation. These are the optimized preparative parameters of MOBI CuSE4 thin films by vacuum evaporation. Precursor is MOBI CuSE4, melting point 75, deposition rate is pressure, current, and growth substrate temperature, which is at room temperature. This is the optical absorption studies. Optical absorption spectra of as deposited and vacuum annealed MOBI CuSE4 thin film, and in figure number 8 shows plot of h mu square versus h mu for MOBI CuSE4 thin films shows for as deposited and vacuum annealed 1.92 electron volt and 1.68 electron volt respectively. This is the X-ray diffraction studies, XRD patterns of as deposited and annealed MOBI CuSE4 thin films. Surface morphological studies. SEM image shows A and C that as deposited samples are quite uniform in nature, and D FESEM image reveals identical morphology to that of previous SEM images, also spherical grain having 250 to 300 nanometer in size. In surface morphological studies, SEM images, it clear that the previous smooth surface has been converted into flex-like morphology. Now, lower magnified SEM image shows the flakes are distributed overall surface with uniform distribution of sizes. The calculated average size of a single flake is around 1 micrometer. Higher magnified SEM images shows these flakes are in magnosize with well-defined walls. This is the surface morphological studies. Image A shows FESEM image clears that the flakes having well-defined walls with 100 nanometer wall thickness. Also, these nano walls are grown vertically to the substrate. And in the figure B shows the vertical thickness of the nanoflakes has been calculated using cross-section FESEM, and the thickness of the sample is 1.8 micrometer. Now, in this surface morphological study shows SEID pattern shows single crystallinity of MOBI CuSE4 nanoflakes. In figure B shows vacuum annealed MOBI CuSE4 sample, very identical morphology with FESEM. The wall thickness is about 100 nanometer diameter. C and D HRTM images shows periodic arrangement of atom to form the atomic plane confirm the formation of MOBI CuSE4 thin films. In compositional analysis, XPS spectra of MOBI CuSE4 thin film, survey spectrum of sample, B shows core level spectrum of MO, C core level spectrum of bismuth, and D shows core level spectrum of copper, and E core level spectrum of selenium. This is the conclusions. Molybdenum bismuth selenide thin films were successfully deposited on conducting and non-conducting substrate by hybrid technique. Optical absorption studies reveal that on annealing, the optical band gap decreases from 2.07 electron volt and 1.87. X-ray diffraction pattern of vacuum annealed MOBI to AC5 thin films shows rhombohedral nanocrystalline structure, and TEM and HRTM's results show highly crystalline structure indicating nanocrystalline nature of MOBI to AC5 thin films. X-ray photoelectron spectra of MOBI to AC5 thin film shows presence of molybdenum bismuth, oxidation states of metals and selenium oxidation state of chalcogen ion confirming formula MOBI to AC5 of deposited material. Molybdenum bismuth copper selenide thin films were successfully deposited on conducting and non-conducting substrates by hybrid techniques. Optical absorption studies reveal that on annealing the optical band gap decreases from 1.92 to 1.68 electron volt. X-ray diffraction pattern of vacuum annealed MOBI CVC4 thin films shows rhombohedral nanocrystalline structure. ACM images of annealed sample shows Nahven nanoflake-like morphology which possess high surface area. TEM and HRTM results show nanoflakes with single crystalline structure indicating purity of MOBI CuSE4 thin films. X-ray photoelectron spectra of MOBI CuSE4 thin film shows presence of molybdenum, bismuth, copper oxidation states of metals and selenium oxidation state of chalcogen ion which confirms formula of molybdenum, bismuth, copper, selenide thin films. Thank you.